So class, now that we have derived the Michaelis-Menten equation, and don't forget, no derivation on any examination, we found out that the Michaelis-Menten curve gives us Vmax and Km. However, the double reciprocal plot is a much better way to get Vmax and Km. The y-intercept is your Vmax. The x-intercept is your K sub m. Don't forget the y-intercept, you have to flip it to get Vmax. The x-intercept, you have to take the negative reciprocal to get K sub m. So we have situations where either drugs, chemically synthesized, or just naturally in the body, we have ways to inhibit enzymes. Okay? So these are either drugs or metabolites naturally found in the cell that will adjust or modulate the Km and Vmax values. So there are three types of inhibition that we will focus on. The first one, in my opinion, is the easiest, and that is competitive inhibition. And the reason why I articulate this as being the easiest is because of the term competitive. Okay? The term competitive. Okay? The term competitive implies that there's a competition for binding to the enzyme's active site. And in fact, that's really what is happening here. So let's go back to our Michaelis-Menten equation. Enzyme plus substrate. Okay, this has a rate constant for the forward direction. This has a rate constant for the reverse direction. Goes to enzyme substrate, which then breaks off into E plus P. We call that Kp. Again, I will reiterate the subscripts don't matter. And another thing, we don't worry about the E plus P going back to ES. We don't, or we just null the reverse reaction at this step. So this is something that we derive the entire Michaelis-Menten equation from this, given our steady state assumption and a couple of other assumptions. But what happens if we throw in a competitive inhibitor into the mix? All right. So if we throw in a competitive inhibitor, the competitive inhibitor competes with the substrate to bind to the enzyme's active site. Okay, so hence competitive, we're talking about an actual competition. All right, so this is why, in my mind, this is one of the more easiest inhibitions to try to study. There's not a lot of confusion. Okay, so we have this competing reaction, which gives you EI. Okay, EI cannot dissociate into products. ES can. The only way EI can dissociate is if we know the dissociation constant, I'll call this Ki prime, of the reverse reaction. And that will have its own rate law. Okay? And that rate law, though it's not going to be very important, I'll just put it, rate is equal to Ki prime times the concentration of EI. So that rate law and that dissociation of EI back to free I and free E can be zero order, first order, or second order. But the magnitude of this dissociation constant Ki prime tells you whether you'll have free enzyme available to bind to substrate, to form the enzyme substrate complex, and in turn generate free product and free enzyme to catalyze the reaction over again. So instead of having the orange, we are now in competition with the purple reaction. All right. So what is the net effect of this in the Lineweaver-Burk plot? We'll focus on the Lineweaver-Burk plot simply because we get better information of that. With that, it's much easier to determine Km and Vmax than using the Michaelis plot and trying to maneuver the hyperbolic curve. All right, so let us draw the Lineweaver-Burk plot. I will draw it over here. Okay. This is competitive inhibition. And we'll do a Lineweaver-Burk plot as I have stated before. So first of all, as always, okay, label your axes. Okay, label your axes. And what are the axes or the correct axis labels for a double reciprocal Lineweaver-Burk plot? All right. So if you said 1 over V, 1 over V sub naught on the y-axis versus 1 over S on the x-axis, then you are correct. All right. And so what is the Lineweaver-Burk plot will look like without the addition of an inhibitor? Okay, it's going to be a straight line. So we will have the straight line. I'll just use this ruler here to mark my straight line. Okay. And this is without the presence of any inhibitor. So this is without inhibitor. What happens if you do have an inhibitor? Okay, one of the things that you have to recognize is any inhibitor, whether it's competitive, as in this example, or non-competitive, or uncompetitive, okay? What it will do is it will shift the curve counterclockwise, all right? It will shift the line counterclockwise, and in a pure competitive inhibition, it's going to shift it So the first thing to realize is to, when you make your Lineweaver-Burk plot, is to get the right axis labels. So for the y-axis, that will be 1 over V. And for the x-axis, that will be 1 over the substrate concentration. So a competitive inhibition, the Lineweaver-Burk plot without the inhibitor is going to be the same. Okay, it's going to be a straight line. Okay, that is without the inhibitor. But what you should know is that regardless of the type of inhibition, whether it's going to be uncompetitive or a special case of mixed inhibition known as non-competitive, whatever type of inhibitor you have, competitive, uncompetitive, or mixed, non-competitive is a type of mixed inhibition. Whatever inhibition you have, it's going to cause that line to shift counterclockwise. Okay, it's going to cause that line to shift counterclockwise, and for a pure competitive inhibition, the line will shift with a common y-intercept. Okay. So this line is, the black line is no inhibitor, and the red line is with a competitive inhibitor. Okay, the presence of a competitive inhibitor. So now our 1 over V max is shared with the V max with the competitive inhibitor. We'll call that the apparent V max. Okay. However, with no inhibition, our minus 1 over K sub m is here. Our new K sub m has shifted here. So now we have a new minus 1 over apparent K sub m. Okay. Now let's go back to our Michaelis equation. Okay. The Michaelis-Menten equation tells us that V sub O is equal to V max concentration of S divided by Km plus the concentration of substrate. All right, so that is with no inhibition. Once we have an inhibitor, so this is with no inhibitor. Once we have the presence of an inhibitor plus inhibitor, in this case plus a competitive inhibitor, our V sub O is going to change. Okay, our new V sub O will be changed based upon the concentration of the inhibitor that you added, but also don't forget that it will also be dependent on the dissociation constant Ki prime that gives you free I and free E. So in the presence of an inhibitor, we have V max concentration of S divided by alpha Km plus the concentration of S substrate. So now we have a modulator known as alpha that modulates your Km. So this alpha will actually equal to 1 plus the concentration of the inhibitor divided by the dissociation constant Ki prime. All right. So that is the modulator. Okay. Increasing alpha would mean an increase in the counterclockwise turn of this curve. Okay. So what will cause more of a counterclockwise turn? An increase in the concentration of the competitive inhibitor that you've added. That will cause this to have more of a counterclockwise turn. So it's a counterclockwise turn. What else would cause this to turn more counterclockwise? Okay. What else would cause this to turn more counterclockwise is if you have a very high value of your dissociation constant. Okay. So the dissociation constant Ki prime gives you the amount, a very low value of the dissociation constant means that you have more enzyme in the form of EI. So a low dissociation value constant means that you're kind of stuck at the enzyme inhibitor complex. So this is not something that I would emphasize or I'm going to test you on, but a high concentration of high concentration of inhibitor and a high dissociation a low dissociation constant. A low dissociation constant, that value will tell you that if you have low dissociation, that EI tends to stay at EI. If you have a high dissociation constant, that EI will tend to dissociate to free I and free E. A low dissociation constant means that this will not dissociate, it will stay at EI, and whatever EI you generate in this equilibrium will remain at EI. Okay, so this alpha modulator, okay, is modulated and depends on the magnitude of your dissociation constant. A low Ki means a high value of this fraction. A high concentration of inhibitor means you have a high concentration for this fraction and henceforth a high value of alpha. High values of alpha means more counterclockwise shift in your Lineweaver-Burk plot, but more counterclockwise shift this way also implies more of a shift this way, affecting your apparent case of M. Okay, so I'm not going to go into too much detail in terms of test questions on this alpha, but I just want to point it out there and tell you that you now have a situation where before, let's go back to our Michaelis-Menten equation, before everything without inhibition was just fine and we derived this equation previously in our lecture, at the video lecture, but now with the competitive inhibitor, our case of M has modulated, okay, and that modulation is dependent on this alpha factor, and the alpha factor is 1 plus the concentration of the competitive inhibitor divided by the dissociation constant. Okay, so the high concentration of inhibitor, the low dissociation constant, all of that is a contributor towards high alpha and better inhibition. So that is competitive inhibition. A hallmark is the common y-intercept, which implies one thing, and one important thing is that Vmax will equal to V apparent max. Okay? So the competitive inhibitor does not change Vmax whatsoever. The only thing it changes is the Km to a new apparent case of M. All right? So how is that possible? Okay, that your Vmax remains the same. Well, it's best if you learn this from a picture, from a pictorial standpoint. So let me rotate this way. Okay. So the very nature of a competitive inhibitor, here is our enzyme, and terminus, C-terminus, the proper fold and domain, and everything is there. Here is the cognate substrate, S, okay? But now in a competitive inhibitor, I have competition to that active site, okay, with my competitive inhibitor I. All right, so we have a competition here. All right? So the way to overcome competition and to dilute out this inhibitor and negate its effect to the enzyme's active site. All right, how do you overcome it? Okay, it's very easy. The way you overcome this is you add more substrate concentration. Okay, you add more substrate molecules. And just by sheer Brownian diffusion, okay, you dilute out this inhibitor. So even if I have 2 molecules of inhibitor, and notice it has the same shape, lock and key, or induced fit, it has the same overall 3-dimensional shape to go to the enzyme's active site. But regardless, I only have 2 molecules of the competitive inhibitor. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 molecules. We'll put a 10th molecule here of the actual cognate substrate. So the substrate will actually win in competing out and win in the competition for this enzyme's active site. Okay, so you're actually shifting this equilibrium. You're shifting this equilibrium more towards the enzyme substrate complex, which in turn makes free product. How are you shifting it? You're shifting it by saturating the system with more substrate, shifting the equilibrium this way. Okay, shifting the equilibrium this way towards the formation of enzyme substrate complex and henceforth product. All right. So this is a competition, and you win in a competition by brute force outcompeting your inhibitor. So in this regard, let's come back to our Michaelis plot. Okay. Concentration of substrate on the x-axis, V sub O on the y-axis. The way you overcome competitive inhibition is you are in this regime. Okay, this regime of the competitive inhibition at that substrate concentration. Okay, you will still achieve Vmax. Now your K of M, okay, that's a different story, okay? To get to Vmax over 2, to get to Vmax over 2, I think intuitively you probably guessed it. Okay, intuitively, okay, you've added more substrate. So now you're going to need more substrate molecules to achieve Km. So our apparent Km has now increased. All right. So you will still achieve Vmax, but you will achieve Vmax at a higher apparent K sub M. Okay. So the V sub max stays the same. Okay. You just add more substrate. Okay. You just add more substrate. So our final comment on this is in the presence of a competitive inhibitor. Let me go here. Actually, let's go this way here. In the presence of a competitive inhibitor, your Vmax will equal to your apparent Vmax. Okay, this is with the competitive inhibitor. This is no inhibitor present in your system. Okay, Vmax is going to equal to apparent V sub max. With no inhibitor, you will still have Km. Okay, but here, in the presence of a competitive inhibitor, you will have a new K of M, the apparent K of M, and that's going to be greater. Okay, so K sub M, apparent K sub M goes up, and the explanation is that it's going to take more concentration of substrate to get to Vmax over 2. So you have to add more substrate to get to V equals Vmax over 2. So your apparent K sub M is going to go down in a competitive inhibitor. Okay, so we had several examples of this in lecture. Okay, for example, methanol and alcohol in alcohol dehydrogenase. That was an example of competitive inhibition. Many of our common drugs, such as sildenafil, the active ingredient in Viagra, is a competitive inhibitor. A lot of drugs, methotrexate, the anti-leukemic drug, is a competitive inhibitor of dihydrofolate reductase. So succinate, malonate are competitive inhibitors of succinate dehydrogenase, some enzyme that is found and very important in the TCA cycle. So look over your PowerPoint notes for examples of competitive inhibition, because there is a ton of them that we went over in class. The statin drugs are competitive inhibitors, okay? And one way to determine if you have a competitive inhibitor is to look for that common Y-intercept, because your Vmax is essentially unperturbed. It just takes more substrate concentration to get to that same Vmax, or to get to that apparent Vmax. You just have to overcome the inhibition, all right? And your degree of competitive inhibition really has to do with how well the competitive inhibitor binds to that enzyme's active site and sticks to the enzyme's active site, okay? And so how well it sticks to it is determined by its dissociation constant. A low dissociation constant along with a high concentration of competitive inhibitor that you started off with really pushes that line in the counterclockwise direction, and really would require more substrate concentration to achieve V equals Vmax over 2. That is, it's going to really increase apparent K sub M. All right, our next type of inhibitor is known as the uncompetitive inhibitor. And the uncompetitive inhibitor, as we go back to our Michaelis-Menten situation, Kf, Kr, this goes to the enzyme substrate complex, which breaks down to E plus P. Okay. The uncompetitive inhibitor really does not compete for the enzyme's active site. So the uncompetitive inhibitor just binds to the enzyme substrate complex. We have a dissociation constant, I'll call that Ki prime, and now we have an enzyme inhibitor substrate complex, sort of a tri-complex, and this is non-productive. So this will be a non-productive interaction. It will not go and make product. So the uncompetitive inhibition that is shown here, this is an example of uncompetitive inhibition. In uncompetitive inhibition, the substrate can still bind to the enzyme's active site. Okay? It can still bind and give you ES. The problem is now you have competition in this direction. Okay? You have competition here. All right? So what does this tell you about the inhibitor versus the substrate? Okay? It should tell you that the inhibitor molecule and the substrate molecule are pretty different in terms of three-dimensional structure. If you want to contrast that with this figure here, you see the inhibitor and the substrate must look alike if they are to recognize the attributes within the enzyme's active site. Okay, and because it's a competition. This is not a competition because the substrate binds to the enzyme just fine, but that enzyme substrate complex is in danger of going in this downward reaction into something that's non-productive. And again, the only saving grace is the magnitude of this dissociation constant. If the dissociation constant is high enough, you can achieve free I and then free ES, which in turn can go and make enzyme and product. So what does this look like in a Lineweaver-Burk plot? Okay, so the double reciprocal plot is what we will do one more time. All right. This is for uncompetitive inhibition. And as always, I want to emphasize the idea of always labeling your axes, and if any type of math is involved, always put a number with the units. Okay. So this is with no inhibitor. No inhibitor. Now what happens if we add a competitive inhibitor? right? So this is the classic case of parallel lines. So let's draw one parallel line here, and then, let's do red. We'll draw another parallel line to that. Okay, so different degrees of inhibition, uncompetitive inhibition. Okay, so remember that any type of inhibition will result in a counterclockwise shift. Okay, counterclockwise shift. So what has now happened to our VM, V sub max, and our K sub M? Okay, now these will be apparent Vmax and apparent Km. Okay? So here is our y-intercept with no inhibitor. We call that 0, that coordinate 0 and 1 over Vmax. Okay, what about this one here for this inhibitor, this uncompetitive inhibitor? Okay, that will also be 0, 1 over apparent V sub max. And the coordinates for this third line, now it could be the same uncompetitive inhibitor in which you've increased the concentration, or it could be a completely different uncompetitive inhibitor that just is much better in its uncompetitive inhibition. So this red line could be the same, we just ramped up the concentration, or this red line could be a different uncompetitive inhibitor with different kinetics. But this one will be 0 and also 1 over apparent V sub max. Okay. What about our x-intercept? This x-intercept is 1 over K sub M and 0. Okay, those are the xy coordinates. The xy coordinates for this one is going to be minus 1 over apparent K sub M and 0. And then for this one, the x-intercept here will be 0 minus 1 over apparent K sub M. Okay? So we have a K sub M, apparent K sub M, dependent upon how this shifts counterclockwise. All right. So this can be increasing inhibitor concentration, or like I said before, two different uncompetitive inhibitors: uncompetitive inhibitor 1, uncompetitive inhibitor 2. All right. Obviously, increasing inhibitor concentration, more uncompetitive inhibition. All right. So how is this modulated? Well, it's modulated the same way as before. Okay. We still have that alpha modulation, and this alpha modulation is going to be 1 plus the concentration of the uncompetitive inhibitor over the dissociation constant Ki prime. Okay, so that modulator is still going to exist. All right. So this alpha, which represents the degree of uncompetitive inhibition, we can call it alpha prime if we're going to call the alpha modulator for competitive inhibitor alpha. We'll call the alpha modulator for uncompetitive inhibition as alpha prime to discriminate that from alpha, which we see in competitive inhibition. So higher the uncompetitive inhibitor, more inhibition, because this fraction gets larger. Lower the value of the dissociation constant. This is a dissociation constant. Okay, that low value of dissociation implies you're kind of stay more in the EIS triumvirate, and you'll have very little population that will dissociate to ES and free I. So these things are working against you in terms of enzyme substrate complex forming free enzyme end product. All right. So what is happening here? More counterclockwise shift, more inhibition. What is going on in a uncompetitive inhibitor? If we want to draw this pictorially, okay, here is our enzyme. Here's our enzyme's active site. Okay. Well, voila. nice enzyme substrate complex. Unfortunately, we don't get a return back to our free enzyme and our active site ready to get recycled again, and our product P. Okay, after all of that chemistry, what happens is that this can also be a binding site somewhere outside the enzyme's active site. We could have EIS, okay? And if you have EIS, that means you'll have no product, okay? So you can ramp up the uncompetitive inhibitor. Notice the shape that I'm drawing it as. It doesn't really fit. It's incompatible to the enzyme's active site. So I could raise E to, all I could raise I could raise the concentration of I and have 100 molecules of these I's shaped as a diamond. It will not affect the enzyme substrate complex formation whatsoever. The only thing adding more I will do is it will shift away that enzyme substrate complex towards the non-productive EIS. Okay. How can you overcome this? You can't. Okay. You think if you add more substrates, it will affect the binding of the uncompetitive inhibitor? Okay. The answer is no. Okay. The substrate will still bind to the active site groove because the inhibitor binds to someplace else outside the active site. Okay. So in a competitive inhibitor, there's competition, so the enzyme and substrate look alike. In an uncompetitive inhibitor, the enzyme, substrate, and the inhibitor, or I should say the substrate and inhibitor, do not really have to look alike. Or substrate and inhibitor do not really look alike. I'll put that in quotation marks, look alike. Okay? So that is in contrast to a competitive inhibitor where they have to look alike in order to compete to the enzyme, for the enzyme's active site. All right? So what happens in terms of Vmax and case of M? Okay? So this is with no inhibitor. We have V sub max, and we have K sub M. We have the uncompetitive inhibitor. Okay, we have a new apparent V sub max, and that apparent V sub max, okay, is going to be lower. Okay, it's going to go down. And we're going to have an apparent K sub M. And that too is going to be higher or lower. Think about this now. Okay. Is it going to take more substrate concentration to get to Vmax over 2? Or will it take less substrate concentration to get Vmax over 2? So what do you think it's going to be? If you thought about it enough, your Km will also be greater than your apparent Vmax. So your apparent Km. So your apparent Km also goes down. Okay. So that really seems odd that now it's going to take less substrate concentration to achieve Vmax over 2. Okay. So that also implies that a greater affinity of the enzyme's active site for the substrate. Okay, so how does that jive with what we're seeing here? Well, take a look at our equilibrium here. Okay, if you look back at our equilibrium, okay, if we have more uncompetitive inhibitor, you drive ES to form the non-productive EIS. And what does that do to this equilibrium here? It's actually going to force that equilibrium to go this way and make more ES, more enzyme substrate. So it's not that it takes less substrate concentration to get to V equals Vmax over 2. It's just that you're shifting the substrate to bind to the enzyme, forcing the equilibrium to the right. And this is, in essence, Le Chatelier's principle. That is why we don't call it Km, we call it apparent Km. The apparent Km has reduced. The apparent Km has reduced, and that is simply because we have shifted the equilibrium more towards the formation of the enzyme substrate complex. Okay, so so you may think that, oh, you know, the Vmax is greater than the apparent Vmax. Okay, that makes sense. The V apparent Vmax is going to go down. But how does the Km be greater? How does your K sub m increase in the presence of an uncompetitive inhibitor? Okay, well, it's because your apparent, the keyword being apparent, Km goes down. All right, your apparent Km goes down because you're forcing the equilibrium more towards the enzyme substrate complex. Okay. Another way to try to think of this, if you actually put in numbers here, so let's put in numbers. We'll call this -1, 0. We'll call this -2, 0. And we'll call this -3, 0. All right. So for no inhibitor, okay, this is the xy coordinates -1, 0. So for no inhibitor, okay, we take the negative reciprocal of -1 and we get +1. This is -2, 0. So with the black uncompetitive inhibitor, I'm sorry, with the purple uncompetitive inhibitor, the purple uncompetitive inhibitor, we will do the negative reciprocal of -2. The negative reciprocal of -2 is 0.5. And then the red one, the red uncompetitive inhibitor, that one has coordinates -3, 0, so we'll take the negative reciprocal of -3 and we will get 0.33. And you can see the apparent Km has gone down relative to the situation where there is no uncompetitive inhibitor. Okay? So sometimes if you're confused, just put in simple coordinates here. Okay, and take the negative reciprocal. Okay, you can also do that here. Okay, you can do 0, 1 here. You can put 0, 2 for the purple uncompetitive inhibitor. And then you can do 0, 3 for the red uncompetitive inhibitor. All right, and if you take the negative reciprocal of that, you'll get the negative reciprocal of 1 over Vmax is 1. The negative reciprocal of 2 is 1/2. The negative reciprocal of 3 is 1/3. So you can see your Vmax has also, apparent Vmax has gone down. So sometimes it helps just to put in mock xy coordinates here and then take the reciprocal of them. Okay, in case this thing seems confusing. All right, so in an uncompetitive inhibitor, the apparent Vmax goes down and the apparent Km goes down. We talked about some examples of uncompetitive inhibition. The most striking example that we saw was arsenate being an uncompetitive inhibitor of a very important enzyme in glycolysis called glyceraldehyde 3-phosphate dehydrogenase. GAPDH. glyceraldehyde 3-phosphate dehydrogenase. Okay, so this enzyme will come back again when we talk about glycolysis. Our last type of inhibition is a special type of inhibition. Our last type of inhibition is a special type of inhibition. Let's go and write our Michaelis-Menten equation here. All right, so just as a review, we talked about competitive inhibition, where the enzyme will have to compete for its active site binding to either substrate or to the competitive inhibitor. This has a dissociation constant Ki. That was our first example, if you remember. Our second example is where we have an inhibitor that binds to the enzyme substrate complex in an uncompetitive manner. And that one has a dissociation constant Ki double prime. So EIS has a dissociation to ES and I based on Ki double prime. EI has a dissociation constant to E and I based on Ki prime. So this was what we called uncompetitive. This is what we called competitive. Now we'll have an inhibitor that has the modality to bind to both the enzyme's active site as well as to the enzyme substrate complex. And that is called mixed inhibition. Okay, but if the dissociation constants are equal to one another, that is, if EI will dissociate to E and I at the same rate where EIS will dissociate to ES and I, then we will have non-competitive inhibition. Sometimes called pure non-competitive inhibition, but and this is the form that we will focus on because of the ease. The equations come out a little bit easier in non-competitive inhibition. All right. So if the dissociation constant Ki prime is greater than Ki double prime, then it has more uncompetitive inhibitor characteristics. If the Ki prime dissociation constant is greater than Ki prime, Ki double prime is greater than Ki prime, that means that the competitive inhibitor quality begins to outshine the uncompetitive inhibitor quality. So if we keep these dissociation constants at the same, then the quality of competitive inhibitor cancels out the uncompetitive inhibitor quality. But if one is greater than the other, then the inhibitor has more competitive qualities than uncompetitive qualities, and vice versa. The inhibitor may have more uncompetitive qualities than competitive qualities. So all of this really relies upon Ki prime and Ki double prime, that dissociation constant. Right? So what does this look like in a Lineweaver-Burk plot? Okay. So in a Lineweaver-Burk plot, it's going to look for pure non-competitive inhibition. So again, make sure you have your labels proper. So let's the double reciprocal plot. Our x-axis is 1 over s. Our y-axis is 1 over v sub naught. As always, without the inhibitor, we have something like this. So what happens in pure non-competitive inhibition? Now remember, in all types of inhibition, regardless if it's uncompetitive, competitive, or mixed, or a special type of mixed called non-competitive, that presence of I will shift this line counterclockwise. Okay, that presence of I will shift that line counterclockwise. And if you have a pure non-competitive inhibition, this is what you'll see. In pure non-competitive inhibition, you'll have a common x-intercept. So this is in the presence of the inhibitor I. So what does this mean? Okay, well, let's look at our intercepts. We'll look at the intercept for the situation where there is no inhibitor, no non-competitive inhibitor, and that is going to be 0, 1 over V max. And in the presence of a pure non-competitive inhibitor, we have 0, 1 over apparent V sub max. Okay. But if the dissociation constants are the same, then this coordinate will be minus 1 over k sub m comma 0, and it will also be minus 1 over k sub m comma 0, apparent k sub m for the situation with the inhibitor. Okay, apparent k sub m. So we have 1 over apparent k sub m, and then 1 over k sub m, minus 1 over k sub m. So what has happened here in pure non-competitive inhibition? Okay. In pure non-competitive inhibition, your k sub m remains unaltered. All right. So if we were to summarize our findings, okay, so no inhibitor, and then here we have the presence of a non-competitive inhibitor. Okay, no inhibitor, we have V sub max. In the presence of a non-competitive inhibitor, we have apparent V sub max. And looking at our graph here, if 1 over V sub max has gone up by this much, from here to here, if 1 over V sub max has gone up by that much, that means V sub max has gone down by that same amount. So 1 over V of max goes up, V of max goes down, so the apparent V sub max has gone down. And then with no inhibitor, we have Km, the Michaelis constant, substrate concentration where V is equal to V max over 2, and then we have an apparent K sub m. And as you can see, in pure non-competitive inhibition, they actually equal to one another. All right. The common x-intercept means they equal to one another. So the substrate concentration to achieve V max over 2 is unaltered. Okay, this is provided that you have pure non-competitive inhibition. Okay. Okay, pure non-competitive inhibition. So going back to this, all right, the key caveat is Ki prime equals Ki double prime. So every time this dissociates, this will dissociate. So your Km, which is the substrate concentration, where V equals Vmax over 2, is really unaltered, okay? Because we would imagine this going at the same rate as this going, so your Km is essentially unaltered or unbothered by the presence of a pure non-competitive inhibitor. In real life, when you have real mixed inhibition, okay, where if you have where Ki prime does not equal Ki double prime, okay, in that situation, okay, where they do not equal one another, then your Km will either increase or decrease, okay? And in that situation, the intersection point, okay, will not be at the x-axis, but it will be somewhere here in the second quadrant. Okay, so this hash lines or this striped lines would mean the intersection point. If the dissociation constant of the competitive inhibitor aspect of your mixed inhibitor does not equal the uncompetitive inhibitor aspect of your mixed inhibitor. So it's going to intersect somewhere here in the second quadrant. Okay, and dependent on where it intersects in the second quadrant, your Km will either increase or decrease. Okay, your actual Km, your apparent Km will actually increase, okay, if this Ki, this dissociation constant. Okay, remember, a low dissociation constant means that it's going to stay in that form. It's not going to dissociate. So a low dissociation constant for Ki prime implies that this will have more of a competitive inhibitor in it. Okay, or a low dissociation constant for Ki double prime would mean that this enzyme would have more uncompetitive qualities to it. So dependent on which varies, your Km can increase. That is, if your mixed inhibitor has a low Ki prime. Or your Km can decrease if your mixed inhibitor has a low Ki double prime. Okay? So just think about that for a moment. All right? If your Km increases here, when it intersects in the second quadrant, if your Km increases, where did we see an increase in apparent Km? In a competitive inhibitor. So that means your dissociation constant for this guy is very low. It likes to remain EI. Okay, so your Km or your apparent Km will go up. If your apparent Km in the presence of a mixed inhibitor goes down, where did we see apparent Km go down? We saw that in an uncompetitive inhibitor. So if the apparent Km goes down, that means this dissociation constant is much stronger, so it's going to stay at EIS, and your apparent Km will go down. All right, so you can see it's very confusing and can get complicated because the mixed inhibitor has both competitive properties and uncompetitive properties. But you can see how easy it is if we equate these dissociation constants and get pure non-competitive inhibition, then you just have the situation as depicted here, okay, where they intersect simply at the x-axis. If I were to draw pictorially what is happening here, okay. Here is my free enzyme. Okay, here's my active site. Okay, here is my substrate. Okay. Okay, substrate goes in just fine. Okay, substrate goes in just fine. However, I do have this problem here where this inhibitor can come in and mess up my product formation. Okay, and that will lead me to EIS, which is not good, the non-productive complex. But I have another problem here, okay, and that is this. Okay, I have this guy, my inhibitor, that could come in and give me this. Okay, so this inhibitor molecule has the capability of binding to this site as well as to a site outside. So this may be a little bit misleading, so I'll just put in terms of the geometry, so I'll just put this here. Okay, I'll just draw the inhibitor like that. So the inhibitor with a shape that's compatible with the active site and a shape that's compatible to someplace outside the active site into the enzyme substrate complex. Okay, so the shape of the inhibitor is compatible with the active site and also outside the active site. Okay. So we have all of this going on here. Okay, we have the uncompetitive in our mixed inhibitor properties, and then we have the competitive mixed inhibitor properties. Okay, competitive inhibitor properties in our mixed inhibitor. All right, so this is non-competitive inhibition. The most important point to realize is that non-competitive inhibition is a special type of mixed inhibition. Okay, so I cannot emphasize enough how you need to realize that we are talking about a subset of mixed inhibition, and that's called non-competitive inhibition. So this is a special type of mixed inhibition. So there are several examples of non-competitive inhibition. The beta-lactam antibiotics is one example. The angiotensin converting enzymes, those are known as ACE inhibitors. Okay, those are non-competitive inhibitors, okay, or you can call them mixed inhibitors. Okay, so blood pressure and lowering enzymes or drugs. Your PowerPoint book slides has a couple of examples of mixed enzyme inhibition. Cyanide inhibiting the electron transport chain is another example. Azides. Some metals are mixed inhibitors. But anyways, the point is, key point, non-competitive inhibition is a subset of mixed inhibition. So non-competitive inhibition is a special type of mixed inhibition where we equate these two dissociation constants. When we do that, we have a situation where we have a common x-intercept. Our Lineweaver-Burk plot gets shifted counterclockwise as it does in all types of inhibition. And in a mixed inhibition or a pure non-competitive inhibition where Ki is equal to Ki prime, the Vmax goes down, apparent Vmax goes down, apparent Km goes down. All right, one final point is do not forget that we are talking about apparent Km and apparent Vmax. So anytime there is the introduction of an enzyme into the mix and we want to quote a Km or Vmax, okay, so please use apparent Vmax and please use apparent Km, okay? This is any time you're dealing with a problem that has an inhibitor with it. Once you put in an inhibitor, competitive, uncompetitive, or mixed, non-competitive, okay, the new Vmax becomes apparent Vmax, the new Km becomes apparent Km. All right. So that is it. the different types of inhibition, let us just basically review. We have one situation where you have a common Y-intercept, competitive inhibition. We have a situation where you have parallel lines, uncompetitive inhibition. And then we have a situation where you have a common X-intercept. So common Y-intercept, parallel lines, and now a common X-intercept. All of those stand for, respectively, competitive inhibition, uncompetitive inhibition, and pure non-competitive inhibition, which is a special type of mixed inhibition. Thank you.